the challenges of the multi-core. So we have different type of multi-cores, and each architecture, each type of multi-core would have its own case. So there is no single solution that we can provide or we can talk about. And that's another reason that CAS32A, it's presented itself as a very generic, not dependent on any specific architecture of multi-core. So you could have a symmetric multi-core processor with one RTOS basically managing the partitioning, managing the robustness, timing, and resources, or you could have asymmetric partitioning with real-time operating systems loaded to each core. And how that real-time operating system is governing the OFPs or application software are very different and unique for each case. So why do we have to deal with this multi-core? Well, there is two reasons. I believe the main reason is the industry size and industry evolution. Avionics domain compared to other gaming, automotive is a very tiny market, and the market moves forward. So we have the obsolescence of the single core, very difficult to get those these days. So we as a avionics domain, our engineers, we have to follow this realm. In addition, we are moving forward from the federated system to more of our IMA concepts, and then more up into the cabinet-based advanced avionics. We're going to put more functionality into our in each card. So capability increases and the higher demand of the speed and multi processes and applications. So for those two main reasons, we have to address this, and certification authorities, FAA and EASA, have provided guidelines for this purpose. If you ask the manufacturer about the interferences, which is the main topic of this webinar, they would say, well, those are the performance bottleneck. And if I ask you guys, all audience here, you would say, especially the safety folks on this webinar, you would say these are dysfunctional behavior. But the goal is that these failure modes related to this shared resources or interferences, they could have caused loss of integrity or availability of the systems within the aircraft. So if you go back to the single core or the typical avionics, the safety concept starting from the FHA, PSSA, SSA, and the fault tree analysis still is valid and needs to be done from a top-down and bottom-up approach applies to the MCPs or multi-cores. More difficult so, especially when you move to a design assurance level A, DAL A. Okay, so the issue is the lack of predictability, right? The fail-safe principle that should prevent a single hazards or single fault to create a catastrophic or hazardous situation has to still be intact. Microprocessors, the multi-core processors do have different type of what we call the black box components in terms of peripherals that could create those type of interferences. And we also have to deal with their complex configuration settings and make sure that those are documented and those are safeguarded for high criticality level of the systems. Well, the reason we have to deal with that is the safety. Every avionics systems have to finish their task or functions within a deadline, within an allocated time. And when you add all of these complexities, a missing single deadline could cause a catastrophic effect. So we have to deal with that. In terms of the compliance, we should have a software architecture and a hardware architecture in mind. So there should be a system approach. CAS32A imposes and requires to implement a robust partitioning, especially when you apply real-time operating systems to your software and to your implementation. And at the end, deterministic behavior of microprocessors are in question. So in terms of the challenges, the good news is that CAS32A really provided a good guidelines. There are certification memorandums by EASA, and there are informal or formal industry groups that are developed to discuss this usage. Multicores have been certified in avionics, mostly PowerPCs. Some may be Intel-based, different types in terms of heterogeneous or homogeneous, even multi-threading with disabled or enabled. So each scenario, as we said, they're very different. CAS32A indicates that applicability of these objectives to cover the safe behavior of these processors should apply to design assurance level C and above. Okay, some of the microprocessors are exempt, and those are the lockstep nature of some of the microprocessors. And CAS32A does not talk about dynamic feature allocations of the software or hyperthreading. So those, if you are using such cases, you need to discuss, and probably you get an issue paper from FAA or EASA about how you are using that in your architecture. So there are many options, there are many different configurations, there are different partitionings in terms of the item design assurance level assignments. The chip technologies make a huge difference in, or dictates to you in terms of your implementation. So we need to plan ahead, you need to consult with your certification authorities and apply proper tools and methods to prove that your timing analysis and data control and control coupling analysis still holds within this multi-threaded multiprocessor usage. When we look at the CAS32, there are 10 generic or over umbrella objectives, and most of those, they apply in terms of the planning. So those goals. I've color coordinated this slide. So the boxes with the orange text applies to design assurance level B and A. Everything else that has the brown background and the white text applies to all design assurances starting from C and above. So we're going to talk briefly on each objectives and give you some pointers, and then Mr. Bernat will take on the timing analysis challenges and how Rapita Systems can provide solutions. So the first one is two objectives: planning. We should capture these type of plans ahead of time in our PSAC plan for software aspects of certification, and or in our PHAC plan for hardware aspects of certification. So typical things that we should consider is who is the manufacturer of the microprocessor, what is the how many number of active cores we're going to be using, if we're going to be disabling some of those, what are the software components that are hosted on the microprocessor, and if your selected multi-core will be used in an IMA platform and how it's going to be used. Okay, if you're a platform provider or you are hosting your application on IMA that uses a multi-core. So that's the planning number one objectives. So we have to define methods and tools that we'll also use for verification aspects, typical things that we capture in the PSAC or PHAC. One step further than that is planning number two objectives, MCP planning 2, talks about, now that we have identified at the architectural level, let's dive a little bit more in detail and talk about type of resources, cache, RAM, and how those are allocated to different partitions and different cores, and any unique features of dynamic hardware allocations that could be changing the frequency of the clock It could be that the microprocessor can decide to deactivate a core to save some energy. So those are some of the advanced features of the microprocessor that needs to be discussed up front and planned for it. The next two sets of objectives, one that it says usage 1 applies to design assurance level C. It says what type of configuration settings, and there are many different aspects to this that we're going to be used to configure this microprocessor. So those needs to be defined. Some of those could be the pin settings depending on the voltage on a specific cores. And basically that configuration settings, if of those that are familiar with version C of DO-178, we call those parameter data item. So it is considered as a parameter data item. The configuration settings need to be tested, need to be validated, and then need to be protected. Okay, so we're going to talk about those in the next set of objectives. Usage number 2 applies to level A and B and says, okay, for those configurations that you are setting, how you're going to provide mitigations to that so that these are not changed accidentally. Okay, so error preventions and error detections mechanism. Both of these aspects needs to be captured and discussed in your top level plans. The usage of the configuration data should be captured as a high level requirements and then analyzed, tested, verified, and validated later on in your verification steps. Different type of resource usage, and that is a starting of interference channels. What are the paths and how these channels can cause by shared memories, the interferences, the use of cache level 2 or 3, I/O cards, and the interconnects between the cores. And then you provide the verification methods in your verification plans. Both of these aspects of the objectives applies to level A and B. On number 4, we also have to provide available resources and verifications that methods that should be applied to make sure that each resource stays within their allocated budget, especially with timing and worst case execution timing, which Dr. Bernat will cover, is the most important aspects of this multi-core usage. Okay, there are various aspects various places you can capture this. It starts from the top level, identification of the requirements, and then provide solutions for verification methods. To identify these interference channels, okay, they are basically the CAS 32A talks about 3 things. What are the paths? What are the performance of each interface analysis to tag each interface channels? And what are the and then you categorize them into 3: acceptable interference, unacceptable, and then unbounded or faulty channels. And then you have to provide mitigation mechanism. The interface paths can be very complex, okay? This, on the left side, you can see a very simple overlapping applications that could have interference between each other. But on the right side, you can see that for a microprocessor that has certain components, the number of interference channels can increase exponentially up to millions. And by robustness or exhaustive tests, we cannot really prove it's basically impossible. So for the timing analysis. The middle section of this objectives talks about MCP software 1 and 2, and these are really the verification aspects of your multi-core usage. So up to now, we defined the configurations. Up to now, we defined the type and how we're going to use the resources of each microprocessor, of each core. But now, MCP1, software 1, talks about worst case execution time analysis between the software components, and MCP2 talks about the data control and control coupling analysis by executing your requirements-based test. We're not going to discuss the data control coupling analysis. Even CAS 32A does not detail any specific guidelines. You can follow DO-178C approach for that, but then the contention and interference really impacts how the software executes on different cores. And CAS 32A provides two different or kind of overlapping options. One is that we're using a real-time operating system that provides a robust partitioning in terms of robust timing and robust memory allocations and usage. If so, then the application can verify the worst case execution timing separately from the other components. If we're not using a robust partitioning, then we have two scenarios under option B. Either we have interference channels that are mitigated, and we have to show that is mitigated by safety analysis, by architecture. If so, it is similar to option A. But if they are not mitigated, then it's almost impossible, because the worst case execution time should be tested and analyzed using all components running on the actual target, which is extremely difficult, as Rapita team will explain. There is an exception in all of CAS 32A, and that talks about if you are design assurance level C, and all of the software and all of the hardware that is hosted by the platform has the same item design assurance level C, and you are not required to provide robust partitioning. If we're not required to do robust partitioning, we don't have to define the resource usage 3. So if we don't have to do that, we don't have to do the analysis. So that's the exception rule, that we don't have to verify it as a MCP software 1, and we don't have to define the resource usage if everything, all the IDALs, all the software and hardware, by safety, by FHA, shows that you are a DAL C. Okay? If one of the components is a DAL B, we have to show for each components this usage and verification of those. The last two objectives of CAS 32 talks about error handling, which is a concept of the safety net that assumes that microprocessors, the multi-cores, will misbehave. So we assume that it's going to be a failure. We assume there will be a contention. We assume we're going to have a deadline missed. So we have to provide mitigations, and those type of mitigations could be done with different implementations, such as monitoring, redundancies, control functions, and it can get really complex for design assurance level A and B. Lastly, like you're doing on your single core, you have to summarize your analysis and approach in an accomplishment summary, whether it's a software accomplishment summary or hardware accomplishment summary, and show that you met the objectives that you defined in your top level plans. That, at this point, is a summary of the compliance in a nutshell. Again, we look forward to seeing you in April 16 in Barcelona for a full day of opening each of these boxes and have a face-to-face discussion. With that in mind, I'm going to pass the baton to Dr. Bernat to explain the multi-core timing analysis.
Thank you very much. Thank you very much, Reza. Right. So the shift of the presentation now is going to move of understanding more what is an interference channel, how it gets characterized, and identifying some of the challenges to performing that interference analysis. The ultimate principle, if you want, that we just try to reflect over a couple of years working on this topic is that I get asked questions from time to time about so why do we need to do all these measurements? Why do we need to do this approach? And I sort of summarizing the four principles. One is that there is any approach to a static analysis of or a model of the processor is so complex that in the end you end up believing that the only valid model of the processor is the processor itself, which then leads to the only way to perform the analysis is to perform measurements, and lots of measurements, but also supported by analysis, by an understanding of why you're performing those measurements or your tests. And one of the fundamental requirements, and that's why we like to be involved early in projects, is to make sure that there are some observability channels, some mechanisms to get an understanding of what is happening in the processor. That being able to access performance counters and having a very high capacity and bandwidth download mechanism to collect traces of the executions. And the analysis part then becomes the combination of measurements, evidence coming from the real target, plus a static analysis or a level of analysis that makes sense of that data. The other principle is, going back to what Reza was saying, is that you have to mitigate against something that can go wrong, is that I call it the you shall trust no one, is that every single assumption you need to provide some evidence that is correct. For example, as a starting from the bottom, there are some performance counters and some timing that for which you perform the measurements. These counters, if you are not counting the right things, I'm going to talk about this later, invalidates all the analysis you do later on. But also there is the concept that there are parts of the processes, because these are so complex, that not even chip manufacturers have the expected behavior. You have a typical example where we did an analysis of a PowerPC processor, and when you run the same application in core 0 and in core 1, with the same inputs, producing the same outputs, core 0 was significantly faster. Why is that? Well, that was because when they were competing access to the bus, core 0 always wins. But the spec says that the bus was supposed to be fair. And when we investigated further, we got the comment, oh wait, that was not supposed to happen. So, and that goes to what I was saying before, that if there is an assumption that you can map task to cores, if the timing depends on which core you're running, that can infer or alter completely your analysis and your conclusions. And the final one is, ideally some people say, well, the only thing I want is a tool that you press a button and give me a number. And unfortunately that tool doesn't exist, because there is a part of the process that can be automated, but there's a much bigger part of the process, we're going to go later, which requires engineering wisdom. The one-button solution enables only the part of producing the evidence and generating the evidence and analyzing it in the first place. So, first question number one, first challenge is to identify what are the types of interference, or what they call the interference channels. Now, in all the literature and all the conversations that we'll be having, there is a very clear understanding of what I call the direct interference channels. This is if two applications compete for shared resources, for example, the cache or the contention on the bus, that's why I call it a direct, which is basically saying an application, when it runs alone, like somebody driving on the motorway with no traffic, you take some time to perform an action. If that resource is directly shared, like there's more traffic on the road, you hit some contention. These are the ones which are the easier to enumerate. And that's where I think quite a bit of the work has been done, only focusing on these ones. But there's two more categories that we identify, or I call it indirect and unknown. The indirect ones is when the execution time gets affected by hardware unpredictability in a way that you cannot control, or you cannot have the information to identify that evidence. For example, there are some multicore processors that, rather than having the traditional bus, they have a coronet, a connection fabric, and the routing of messages requests through that fabric is unknown. The algorithms that decide which path do you go, and therefore how long it takes to get from A to B, are unknown. There could be variability on memory latencies and even unknown effects that are not observable. One of the key ones is we call the problem with cache coherency protocols. You may have an application running alone using its reserved cache, but because of the operation of cache coherency protocols, another cache controller may overload by snooping requests the validation, invalidation of particular cache entries. That can cause a block of the operation of the cache controller. So even though we have thought that we have probably assigned all the cache to just only one application, something else, because of this indirect or hidden channel, affects us. And the final one is what I call the unknowns. The key ones are the unknown unknowns, where you have no idea what is not happening. The final example, for example, the P48 impulse arbitration is perhaps the one example. The other one is that has been identified on a particular processor, where when an application was doing a heavy load on the floating point unit, the chip overheated and they decided to lower its frequency. Again, that was another one that was not supposed to happen. That was a design issue that by reallocating pieces on the chip layout, that could be affected. But this is going to get worse. At a recent conference, we were talking to some of the ARM developers, and their position is that the new ARM cores, the CPU frequency is a suggested frequency, for which there are very little control, apart from the CPU is going to do things as fast as it can, but you cannot guarantee beforehand how fast things are going to go. So this reflection on this first challenge is that, yes, interference channels which are direct, these are the easy ones, but the question to ask is, what is the impact of other things that can happen? Things that we know, which are the indirect ones, and the unknown unknowns. And part of the analysis is to understand whether there are any unknowns and be able to provide empirical evidence whether they affect you or not. So, the third challenge, or the next challenge, you are still only on challenge number 2, is the argument that we present to provide all the evidence up to the software accomplishment summary, or the accomplishment summary, is based on a hierarchy of assumptions. The bottom one is, how do you prove that your measuring device is correct? Typical approach of doing this timing analysis and understanding where application has a lot of bus accesses, cache hits, or cache misses, is to use program counters. And we've done some experiments, for example, where we've shown that some performance counters don't count what they are supposed to count, and what they count, they don't count it right. Some of them they do okay. But if the underlying evidence is based on being able to show that this application does that many number of cache of hits or cache misses, we need to understand whether that mechanisms work correctly. Then the second level of assumptions is the assumptions which the applications rely on. So as Reza said, if your architecture provides some temporary isolation, then you do not have to do some level of analysis. If there is no temporary isolation, then the final system needs to analyze the full configuration together with all the interference channels. So that's very nice and good, but how do you prove that your mechanism to provide temporary isolation is effective. It may be that it works correctly in most situations, but there is a hidden channel of interference that may actually affect it. And this is where the boundary between the evidence provided the authors, for example, and then the evidence that the applicant needs to provide is important. The authors will provide you as part of the sale pack the evidence of and all the tests about the behavior of the processor, but it's ultimately the applicant that needs to provide that evidence. Let's assume you get that evidence, then you put other petitionings on top of that. Also, that needs to be recorded. And finally, is other issues that other assumptions, for example, that well, we do not suffer any interference because we have disabled all the interrupts, so we disable all these devices. Multicore processors tend to have a mind of their own, and sometimes devices that are supposed to be disabled, they are not. So having a systematic approach to be able to formulate these assumptions as hypotheses and providing in a systematic way the evidence to produce the evidence that the assumptions are correct is part of the fundamental part of the process. The final reflection is that one of the assumptions is that you test the software in the final configuration, except that we've seen so many times that small changes on the software, it can even be as simple as just the recompiling with a tiny little change in the source code, can have dramatic impacts on the execution times. Sometimes they do, sometimes they know. So an understanding of how sensitive is the execution to changes in the software and having a systematic way to see this robustness is actually also quite important. So the key thing is that impact change a small impact, or is a small change huge impact? And then you can put the mitigation strategies on top. So we understand what are the principles, we understand what the interference channels. The first is, the next one is quantification. And it's a well-known technique to, once you identify an interference channel, is generate benchmark. We call them micro benchmarks, so our product is called Rapita, to generate traffic on that particular interference channel to analyze its interference. Now, in the context of multicore processors, the calculation of worst case execution time, which is one of the objectives, is very challenging, mainly because you can throw away any of the purely static analysis models. Even if there was a perfect solution to compute the absolute non-pessimistic worst case execution time, and that technique doesn't exist because it's too complex, but even if it existed, you would probably even not like the number that you get, because the pathological worst case is just so pathological that is most likely not going to happen. So there is a compromise of finding what is the effective method for doing worst case execution time, which can be based on just high watermarks and putting all the emphasis on the testing, or providing a hybrid message or a hybrid method, which is based on part of analysis, part of measurements. In particular, you could then use the technique to analyze what is the impact of whatever method with different degrees of interference, even the maximum interference. So then the idea of this quantifying interference is what I said before. You have your application, let's say it runs alone, and then you put some piece of code on another course that specifically competes with one of the resources. Let's say in that particular case, we have on the picture on the right, you have the micro benchmarks or Rapita that are running on the other cores that also compete for the cache. If the cache is partitioned, you can quantify that this partitioning is effective. If not partitioned, you can quantify what is the impact. And sometimes the impacts are quite non-trivial. So this is the result of one of the experiments on the processors. A processor running alone took about 2 units of time. With one contender, one Rapita, it goes all the way up to about factor of 3. With the fully loaded contenders, multiplication factor on the execution time of your application compared when it runs alone is a factor of 4. And this is quite illustrative. That shows the magnitude of the impact of interference channels. And then how important it is to ensure that there is first a quantification of how big that impact is, and therefore either a mitigation strategies or partitioning by, for example, when a critical application runs, nothing else is running on the whole system, that this approach is effective. The example here, we have a factor of 4. We've seen experimental cases with a factor of 20 and even more than that. So expectations of that the interference channels would not add much interference or variability in execution times are generally underrated. So after this challenge identification, I'm going to put the part of the practical approach. Now, what we are presenting here is our view that we developed over the years. We have borrowed inspiration from a lot of clever people that we've been talking through the years, and that has been distilled into the methodology. So we really haven't invented anything new. We just applied a solid engineering practice to the problem of performing timing analysis for complex multi-core processes. So let's go through these 7 steps that we propose. There's a first step, which is what we call requirements. Worst case execution time is one question, but you need to understand why you need to perform the worst case execution time and in one context. But then when you refine it, there are sub-questions. For example, what is this evidence of, or what is the amount of interference that I can suffer from this particular interference channel? Or I do have robust partitioning. What is the evidence that I have my robust partitioning is effective? And these drives the set of the following activities. The next one after requirements is understand the hardware, and it goes back to one of the objectives of CAS32A, where you formalize that what are the characteristics of the hardware, the configuration, and how that is being used. So once you understand the overarching picture of what is required, what are the activities to be performed, what interference channels and what evidence you need to produce to quantify the impact of these interference channels, the next step is to generate a test design, an experimental design to provide the evidence of quantifying that behavior. Either that the impact is negligible or is bounded or unbounded, and then mitigation, and the mitigation strategies are effective. And this test plan and test design is all the way to these 3 levels. It's engineering wisdom, is engineering approaches, some people sitting down and thinking about the problem. The key part we want to put forward is that the actual implementation of the test and running the test, that is the part that is very cost intensive, and that is the part that can be automated. The idea here is to automate the testing process by specifying what are the questions that you want to perform in the experiments in a quite clear and formalized way, in a very same way you would use specification of tests for unit testing. And those tests that can be run through on the target, generate the evidence in a full automated way, which means that either is a change of configurations or a new question that needs to add it or a new version of the software, the whole evidence can be repeated without costly re-engineering effort. So once you have the tests, this test needs to be run on the target. This requires an integration, getting all the macro measurements, the integrations, all the questions implemented, and data collected. And that's where the automation finishes. Understanding the meaning of the data, understanding and qualifying whether an interference channel is significant enough and whether the mitigation is effective is again part of the engineering wisdom. And all the results get collected into our final results, which is producing the evidence for the certification authorities. So how do we pull out that automation? Now, I've seen plenty of other customers that are working on providing a equivalent of Rapita, which is these micro benchmarks. But micro benchmarks by themselves are not the question or solution. Is one tool of the big building, if you want, that we need to produce. So the way we propose is that you specify the tests using Excel spreadsheets, using the same test format or very variant of the test format that we use for our unit tests. And these tests say, I want to run this experiment, which means I need to run this piece of code, first running alone, and then running with this configuration of Rapita with the other configuration of Rapita, and this is the type of analysis I want. These tests can then be automatically converted into executable code, gets executed on the target. The tools have been integrated as part of the setup process, and then the results being analyzed, and then the next thing the engineer has to do is to look at the output of these results. And the idea here is that the whole process can be repeated automatically. Just for reference, these are the tools that we use in our process. Perhaps the key ones here is the Rapita, which is a whole set of mnemonic adversaries, a set of micro benchmarks. And these are not unique to us. Different people have developed their own ones for their own hardware platforms. The key part of the whole picture is that the value proposition is to be able to do a full automation from the definition of the tests, not just running the micro benchmark, but understanding what do you need to run against what, all the way to producing the results. So I thought that it would be a good way to wrap up both parts of the presentations by being able to represent how the different objectives that Reza has explained map to the engineering approach that we also call it the V model. So clearly the MCP planning 1 and 2 are part of the requirements first stage. In the same way that is resource usage 1 and resource usage 2, which really is the specification of what are the resources that you're using and how they are using it. That educates the next step, which is the understanding part, which is where you define how the key main resource, which is the usage 3. And then the rest of the objectives is part of the final step of the presentation. And I'm just pointing on the screen, apologies, I should actually put it with the mouse, which is the production of the software, the completion summary. But it also is providing the evidence for software 1 and resource usage 4. Know that in order to get to the last box of the diagram, you need to go down the left side of the V, run the test, and go up again. What we are not covering the analysis is anything which is not related to the worst case execution time analysis and interference analysis. So although it is part of CAS32A, we just leave it aside for another process. For example, data control coupling, as far as we've been looked into, is equivalent on single core multi-core. So we have exactly the same challenge. It is the WCD analysis and the timing analysis which is the challenging part. There's Paul Reza, that is one is for you, and talks about CAS32A. And he says, CAS32A guidance paper does not apply when the MCP software and hardware IDALs are all level D or E. What can be used for certification guidance in that instance for DAL D, DAL E?
Well, this is an interesting question. And for a DAL E, there are no objectives even in DO-178. DO-178C or even DO-178 does not have any objectives for the DAL E. You basically develop your functional hazard analysis based on the FHA, the effect of the software or the hazard. It's no effect, and basically there are no objectives to be covered. Now, when it comes to a DAL D, you can reference the purpose of or the objectives, this first section of the CAS32A that says this guidance only applies to DAL-C and above. And then there is another one which is interesting that ties these two together, especially for a DAL-D. If you look at the objectives, verification objectives, chapter 6 of DO-178C, the timing analysis, worst case execution timing analysis, and low-level requirements-based testing is not required for a DAL-D. That is why FAA and EASA took that advice from a system approach to say that this guidance of CAS 32A does not apply. So that's basically the answer.
Thank you, Reza.
You're welcome.
We have another question that I think one is for me, from Jalul, and he says, what is the current status of the product? Is it certified within a multi-core? And what is the associated DAL level? So the answer is no. The tools have not been qualified or used on a certified product for multi-core. Our tools have been certified or qualified up to DAL-A on single core processes. All the tools individually have gone through different levels of certification. What we are putting here is that we're putting a bundle of all the tools together. But no, the multi-core aspect of that has not been done, and that's one of the, completely agree, one of the key things that will be very valuable to go through that process. But thankfully we have Reza on our backs telling us what to do and what not to do. But on that
I think
level,
we've got one more general question that it says if there is any US-based training in place of Barcelona for multi-core. And if you go to ConsuNova website or Rapita website, we typically do July in San Diego and in November in Bristol. And with this one-day multi-core, we've added this to our typical 2 days training workshops. So yes, there will be a July training on this topic in San Diego, and there will be an additional one in Bristol, UK on November 21st of this year.
Okay. Ben, do you have any more questions on the line? I have a final one here. And is a question related to the evidence provided by auto suppliers. It says, why do we have to do this activity if the auto suppliers will provide all the evidence as part of the cert packs? Now, this is a very interesting one because that was exactly the topic of a presentation that we did with Wind River that provided clarification of that issue. And the question is, real-time operating systems, you can get the cert pack, which is the generic pack of evidence, but is still the responsibility of the applicant to use that evidence on the instantiation of the target and your final configuration. And it is the responsibility of the applicant to execute those tests, and in particular perform the quantification of that interference analysis. So in one part, yes, the operating system does provide some level of evidence that can be very useful to a certification, but it is part of the responsibility of the applicant to perform the worst case execution time analysis and to perform the evidence that, for example, the partitioning mechanism or the configuration that provides temporary isolation is effective.